what we've got today is our new topic on multimedia applications. Last week we worked out how a network can support multicast and quality of service control, give priority to different applications. Both useful when we want to support multimedia applications in our network. The first few slides we may go through reasonably quickly because you've covered some of that in ITS413 last semester. We want to define what do we mean by multimedia applications, and then talk about the technologies that we can use to deliver multimedia across the internet. Look and try and characterize multimedia applications, including what their performance requirements are. Look at voice over IP, streaming audio and video, and IP TV. We've already looked at multimedia and quality of service. How can we characterize different applications? Different multimedia applications, that is. Based on the number of, or the number of entities sending and receiving data. That is, do we have one-way communications or two-way communications? Unidirectional multimedia applications we can think of as streaming. You're watching a YouTube video. The video is being sent to you in one direction. You're not sending video back. You may be sending requests for video, but you're not sending video back. It's a unidirectional application. Online or listening, streaming radio or music, watching recorded and even live video examples. Also referred to as streaming. The content may be either stored or live. What's the difference? Stored is, okay, it's on the server that's being sent to you. It's been recorded and saved there. Live is that say the video or the audio that you're watching or listening, the content is being generated at the same time that you want to watch it. A live TV event, watching the World Cup, for example. There's a difference between live and stored streaming. What's the difference? In terms of performance, what's the difference? Or from the user's perspective, what's the difference? You're watching a YouTube video, it's a pre-recorded video. When you press play on that video, from the time when it starts streaming from the server and starts playing back on your computer, so you press play and maybe 5 seconds later it starts playing the video on your computer, that 5-second delay is not a big problem. Okay? All right? Because as soon as it starts playing, so long as it plays smoothly, that small delay at the startup is normally not a problem. So in stored video streaming and stored audio streaming, we can tolerate large delays. But with live, that's not so good, because with live, as it happens, and the content is generated at the server, we would like to receive it and have it played back at about the same time. One example why you'd need that, let's say you're watching a video stream of some sporting event and the audio quality is not good. You listen on the radio, which also has live audio streaming from the radio. Two different sources. Both should be live. If the video is delayed by 5 seconds and the radio audio is delayed by half a second, then you hear what happens on the radio before you see it on the video. And that would be not nice, because you hear that someone kicks a goal and then you see it 5 seconds later. So normally with live applications, we would like much smaller delay from server to client than with stored applications. The other type of multimedia applications are two-way, bidirectional applications, where you interact in both directions. Video calls, voice calls, for example. interactive applications. Sometimes we refer to multimedia applications as real-time applications. By real-time, we mean that the sender and receiver, the two entities communicating, they're communicating as if they're in the same physical location. That is, if I'm talking to someone in the same location, I can have a conversation with someone, and then I am talking with someone over the internet on the other side of the world, we would classify that real time if there's no significant difference in whether we're in the same location or on the other side of the world. Whereas some applications, when there may be a large delay, we may not classify as real time. For example, streaming stored audio may not be classified as real time. Normally with real time applications we need very small delay and very small jitter between source and destination. What's the jitter? Can you define jitter for me? Final exam question. Define jitter. Variation between the delay between subsequent packets. We'll see some examples of that and define it in more detail on this topic. So if we have multimedia applications, what are the other applications? Well, you know plenty of examples. Web browsing, data-based applications. File download, email, database access. Normally in these other applications we care about reliability the most. If I download a file, the file at the server and the file at my computer after I download should be identical. No errors. I don't care so much about the delays and varying delays, not compared to multimedia applications. If I send an email and it takes 10 seconds to get to the destination, I think I'll be happy. If it takes 1 hour to get to the destination, I'll tolerate that. And if it varies over time, I can still survive. So with these data type applications, large and varying delays are okay normally. With multimedia applications, we care about delay much more, delay sensitive. If our delays are too large or our jitter is too large, then our application may be unusable. And our multimedia applications are often loss tolerant. If we lose some data, we can still use the application. Not so when I download a file. If I lose some data, I would need to retransmit and try again. This is something we've seen in a previous course. Voice communications, the spectrum of voice. Majority of voice communications in the order of the first several thousand hertz in the frequency spectrum. Actually closer, up to 10,000 hertz. This gives some examples. The telephone channel can support this range of frequencies. Our voice, speech is typically in this range of frequencies. Music has a wider range of frequencies. When we're talking about data and internet communications, we are talking about sending bits across our network. Our voice is an analog signal, analog input. To convert that into bits, we use modulation. And in the course last semester, we covered in some depth how pulse code modulation, PCM, works. If this line represents our input voice over some short period of time, with PCM we take samples, regular samples, record the value of the input, convert that value into some binary value within the range. So we divide the amplitude into some range and record the value, take a sample and convert that sample into some binary value, a PCM code in this example. And the bits that we transmit are these bits at the bottom. They represent our voice. What happens at the receiver? The receiver receives those bits and does the opposite. They generate the output analog signal. When the receiver receives the bits 0001, it maps up back to the code number 1, which maps back to an output level at this point at the output, and they play back some output analog audio on the speaker at the receiver. And then when they receive the next 4 bits, they play back some output at this higher level, at level 9. And the output keeps varying according to the bits they receive. The main things that impact upon the performance from the user's perspective is the sample rate and the sample size. The more samples we have, the better in terms of accuracy of reproduction at the receiver, and the larger the samples, the better. Low sample rates and small sample sizes can lead to poor voice reproduction at the receiver, and the opposite, if they are high, better reproduction at the receiver, better quality, but more bits to send across the network. And this tries to summarize some of those points, or give a simple example comparing quality against quantity. 6 different, very simple sampled signals reproduced at the receiver. So imagine what's happened. The sender, there's been some analog input, which was a sine wave on the input. It was sampled at some rate and with some sample size. The bits were sent across the link or across the network. The receiver received those bits and takes the sampled bits received and generates some analog output. And these 6 diagrams show the analog output which is produced. So the input, at the source was a perfect sine wave. It was sampled at different points. Each sample was mapped to a number, which then are mapped to some binary value, whatever they are, 0. And those binary values were sent across the link, across our network. The receiver receives the binary data. They know the sample size and the sample rate. They reproduce the signals shown here. What's the difference between them? The difference is the different sample rates and sample sizes. The sample size indicates the number of levels that we divide our range into, our amplitude. The top 3 diagrams show different sample sizes. That is, same sampling rate, 50 samples per second. So if you look at these rectangles here, you'll see there are 50 in that total time period. There were 50 samples. So at the source, we took our input sine wave, and if this is 1 second, during that time we took 50 different samples. Each sample was converted to a binary value. How big was the binary value? In the first case, we took the magnitude and divided it into 100 levels. That is, the number of levels we have here in the first top left diagram is 100. In the middle diagram at the top, we have just 10 levels. That is, instead of many levels here, we just have 10 from here to here. And the last one, just 4 levels. Just probably 1, 2, 3, 4 levels. which means in the last one we need less bits to represent each level. How many bits? Yeah. Yeah. Okay.
What's the sample size? I don't understand.
Let's go back to here. The sample size is this. Each sample we convert to a binary value. How many bits in that binary value? In this example, 4 bits. That's the size of the sample. So why is there 4 bits? In this case, yeah, we have 16 different levels. So every time we take a record of the value, we convert into some, in this case, some decimal number, which converts into a binary number. And we only have, in this example, 16 different levels. We can get the value 0 to 15. Therefore, we need 4 bits to represent one of those 16 values. So the sample size is 4 bits in this example because we have 16 different levels. If I had 32 different levels, I would need, if I had 32 different levels, I'd need how many bits? 32, 5 bits. With 16 different levels, there are 16 different values. We need a 4-bit number, 2 to the power of 4, to represent any of those 16 values. Okay, 0, 0, 0, 0, up to 1, 1, 1, 1. 16 values. The more levels I have, the larger the size of the sample here, the more bits. Now coming back to our different examples here, in the top left, the first diagram, we have 50 samples per second and we have many levels, 100 levels in this case. All right, the numbers I've used here are not so good. They do not convert to binary values. For 100 levels, we'd need 7 bits because 6 bits gives us 64 values, 7 bits gives us 128 values. So in this case, we'd need 7 bits to represent, each sample would be 7 bits long and it would be mapped to a decimal value from 0 up to 99. In the second case, we have just 10 levels. We would need how many bits? 4 bits. With 10 levels, 3 bits can give us 8 levels. 4 bits are needed, therefore, to give us 10 levels. 4 bits give us, in fact, 16 different levels, but to get 10 levels, that is, to represent the decimal numbers 0 to 9, you need at least 4 bits. And in the last case, 4 levels, we need just 2 bits. Which one of the top 3, these are the reproductions of the analog output at the receiver. Which one's better? Which one's better at the receiver? Which is a better reproduction of the original sine wave input of the top 3? The left, the middle, or the right? Which one looks closer to a sine wave? The one on the left, this one. Okay? Everyone can see that this looks closer to a sine wave. Our source had a sine wave input. It was converted into digital, sent across the network. The receiver is trying to reproduce what was input at the source. What it does is it takes the sample and produces an analog output at the level that that sample maps to. And then takes the next sample and produces an output. The more levels we have, the more accurate the reproduction will be at the receiver. We can see that here. Same number of samples, 100 levels, 10 levels, 4 levels. This, well, maybe we can see the shape of a sine wave, but it's not an accurate reproduction of our original. Increasing the number of levels increases the accuracy of the reproduction at the receiver. Compare the bottom 3 now. Here we keep the number of levels the same, 10, 10, 10. But we change the sample rate. And this is, in fact, the same as the middle diagram, 50 samples per second. This is 10 samples per second, less samples over that period of 1 second. And here we just take 4 samples. And when we reproduce at the receiver, we see that more samples per second gives us a more accurate reproduction at the receiver. That is, as we reduce the sampling rate, it gets worse at the receiver. This hardly looks like a sine wave. So in summary, in terms of quality at the receiver, when we want to reproduce some analog signal when it's been sent in a digital form, we get better quality if we have a higher number of levels or a larger sample size and a larger sampling rate, more samples. That is, increase the number of levels and increase the number of samples per second. What's the problem? So if I want high quality output at the receiver for a voice call, at the source I would use a codec that has many samples, a large sampling rate, and has many levels. It's a large sample size. Therefore the quality should be good at the receiver. And I want good quality at the receiver if I'm talking on the phone here and I want the other person to be able to hear and understand what's being said. We'd like good quality at the receiver. What's the problem of using large sample size and large sampling rate?
It needs larger transmission time, so we need more.
A larger transmission time, larger bandwidth. We need to send more data across the link. I'd like to be able to send my voice, same with video, here's an example of a voice. I'd like to be able to send it across the network using as little data as possible, a few bits as possible, so that I conserve the network bandwidth. Let's do some simple example calculations with some of these. The signal is across a period of 1 second. That is, the input was a sine wave generated for 1 second. In the top left, we have 50 samples per second. And we have 100 levels, therefore how big is a sample? How big is a sample? How many bits? 100 levels. How many bits do we need to represent the numbers from 0 to 99? 0 to 7. 6 bits, 2 to the power of 6 is 64. 7 bits, 2 to the power of 7 is 128. So we can represent 128 values with a 7-bit number. We want to represent just 100 values. So we need a 7-bit number. We can't have half a bit. So either 6 or 7. We need a whole number of bits. So to send 1 second of voice using this approach, and it's just a very basic example, we need to send 50 samples per second. Each sample is 7 bits in length. So over 1 second, we need to send 350 bits. So to get this quality, every 1 second I need to send 350 bits across the network. To continue with this non-realistic but very simple example, let's say our network or link had a capacity of 1,000 bits per second. This is our sampling of voice. We're making a voice call using this link, and there are multiple computers utilizing this link. Multiple users want to make voice calls at the same time. How many voice calls can we support in our network? How many voice calls with this quality can we support in our network? How many? Why?
Each one needs 350 bits. We have 1,000 bits.
Okay. Is on each voice call we need to send 350 bits per second. 350 bits in 1 second. So one voice call consumes 350 bits per second. The capacity of our network is 1,000 bits per second. 2 voice calls will consume 700 bits per second. 3 would consume more than the capacity. That is, our network could not support 3 parallel voice calls. So this number, 350 bits, or that was bits, and that was all for 1 second. So in 1 second, 50 samples, 350 bits. 350 bits per second need to be sent. This is the network capacity, 1,000 bits per second. The smaller the requirement for an individual voice call, the more voice calls we could support. Try our very poor quality output at the receiver. We use a different codec, or we use a codec with different parameters where we take just 4 samples per second. Just use 10 levels, 4 samples per second. 10 levels means how many bits per level? Per sample? How many bits? With 10 levels, 3 bits gives us 8 values, 4 bits gives us 16 values, which is enough to represent the 10 different levels. 4 bits per sample, 4 samples per second, 16 bits per second. To send voice at this quality across our network, we will consume 16 bits per second. How many voice calls at this quality can we support in parallel in our network? What is it? $50-something? Is it 1,000 divided by 16 is around 60. $62 maybe, 63. So 62, because we have a capacity of 1,000 bits per second. Each voice call requires just 16 bits per second. We could be sending many parallel voice calls by different people at the same time across that link, across that network. And that's better because more people are happy making voice calls at the same time. So the trade-off becomes that of quality versus the amount of capacity used by a voice call. If we want high quality, we'll use more capacity. We'll need a larger data rate to send at. If we want to use less of the network capacity to send our one voice call and therefore support more voice calls in a particular network, we'd need to use lower quality reproduction at the output. The numbers I've used in these examples are not for real voice calls. We'll see some later, but the same concepts apply. Any questions? Clear as mud?
Sorry?
Is it okay? Clear? Okay. So there's the main trade-off we have with both voice, and the same concept applies for video communications. When we're converting analog information into digital, we need to make this trade-off of how much information, or how many bits do we send, or how many bits do we use to represent the analog. The same applies when you save a file to some, using some codec and possibly also compression. You save some audio as MP3, save a 5-minute song on the hard disk, it takes up, say, 5 megabytes of your hard disk. If you save it at a higher quality audio file as a WAV file, that same 5 minutes of audio, maybe it takes up 100 megabytes. Same audio, the WAV file takes up 100 megabytes, the MP3 just 5 megabytes. Higher quality for the WAV file, but uses up more of the disk space. You can have less songs on your disk. It's the same concept. What do we miss? I think we've summarised that. What is a good sampling rate? Nyquist has a theorem that says twice the highest frequency component. If the largest frequency component in our signal is 4 kilohertz, the sampling rate should be 8 kilohertz, 8,000 samples per second. So typically for voice, when we talk over a telephone line, usually the highest frequency component is limited to 4 kilohertz. So the sampling rate for voice is normally 8 kilohertz, or 8,000 samples per second. It turns out to get reasonable quality voice, the sample size should be about 7 bits, 7 or 8 bits. So with 8 bits, 8,000 samples per second, 64 kilobits per second is the typical amount needed to send good quality voice across a network. That's for voice as an example. We'll come back to voice when we look at how do we send voice across the internet using RTP a little bit later. Audio, when we're not talking about voice, same problems. Audio, when we mean music and so on, non-voice communications, same issues apply. In fact, with audio, often we may desire higher quality output. If you listen to music, as opposed to listen to someone talking, you may enjoy it more if the quality of the output of the music is better than the voice. With voice, we just want to collect the information. With music, we want to hear a different range of frequencies at different qualities. Other than that, the same. What about video? Voice, non-voice audio, video. What's a video? Video, we normally think, is the image part plus audio. And the image part is really just a set of still images or frames which are played back at some rate to represent some motion, some scene in motion. And of course, video is often accompanied by audio. So all video is some image and then some slightly different image played back after some small delay, and another image, such that from our eyes it looks like we see motion. We see things moving. So with video communications, the things that we care about is how big should the frame be and how often should the frame change, the frame rate. For the frame rate, it turns out about 15 frames per second is enough to make our eyes think that we see motion. Okay? So if you have 15 images every second and each image may be slightly different than the other, and you keep playing them, it looks like from our eyes' perspective that the thing is moving smoothly, motion. And most of you, or some of you, if you had fun in primary school or when you're young, you made those you'd draw pictures on the side of books and flip through the books and you would see motion. As you draw some cartoon and different on each page, if you flip through, it looks like you have a video or a movie. So very easy to fool the eye into thinking that they're seeing motion. It's just a set of still images. The other aspect is how big should the frame be, or the resolution. The frame is just an image, a digital image. It depends upon the size, the width and the height of the frame. Because image is just a set of pixels, where a pixel is a colour, a single colour. And to make that image, we just have many pixels and change the colour of those pixels to look what we want it to look like. So we care about how many pixels across, the width of the image, and down, the height of the image, the number of pixels in the image, and how many colours can be represented by each pixel. What about a 1-bit colour depth? What does that mean? One-bit colour depth is just, we have 1 bit to represent each pixel. So if our image is some rectangle, then if we have 9 pixels across and 7 down in this rectangle, and I'd fill in the rest, we have 63 pixels. Each is represented by a 1-bit number, 0 or 1, and therefore we can represent just 2 colours. And the 2 colours we represent normally are black and white. So a 1-bit colour depth is black and white normally. If we had a 24-bit colour depth, then each dot can represent, or is represented by a 24-bit number, which means with 24 bits we can have 16 million different colours in any of those pixels. That is, 2 to the power of 24 is about 16 million. So this pixel may be some colour, some variant of red, colour number on some scale where this represents some colour in some colour spectrum, and the next pixel can be another colour which has a 24-bit value that is 1 of 16 million possible colours. So we have much finer resolution in the range of colours that we can have in our image now. Better quality image if we have higher bit depth in the colour and a larger image. Or for the same size, we have more pixels, a high resolution. So again here, for images, to increase the quality, increase the colour depth, increase the resolution. For video, in addition to the frames, also increase the frame rate to represent motion, to make motion look smoother. Of course, the higher the frame rate, the higher the colour depth, the higher the resolution, the larger the video is to represent the same scene in motion. Because here, with our 1-bit colour depth, 63 pixels, we just need 63 bits to represent that picture. If we have 24-bit colour depth with 63 pixels, we need 24 by 63 bits to represent that same picture. Produces better quality, but is much larger to store on disk and much larger to send across a network. And same with the frame rate. Increase the frame rate. If we had a frame rate of 15 frames per second, then we just repeat images 15 per second. So the total amount we'd need to send to represent that video is every second, 15 frames, 63 bits. Or if we're using 24-bit, 24 by 63 by 15. That's how many bits we'd need to send across the network every second. Or alternatively, to save on your hard disk. So higher quality, more information needed to represent that video. We're going through these quite quickly. Some basic concepts. We want to get into how we send them across the network. One thing that comes into play, especially for video, also with audio, is compression. Well, we have some examples here. Assuming no compression, let's look at some examples in real life for voice and video. PCM voice, if we use our pulse code modulation, the normal recommended sampling rate is 8 kilohertz because voice has frequencies up to 4 kilohertz. Nyquist says sample at twice that rate, 8 kilohertz. So if we sample 8,000 times per second our voice, and a typical sample size is 8 bits, then one voice session or one voice communication consumes 64 kilobits per second, or we need to send at 64 kilobits per second. 8,000 times by 8. So that's an example how much capacity of a network we need to send voice across that network. Just one voice call. What about audio? CD quality audio, music for example, the typical sampling rate is 44 kilohertz. Higher sampling rate because in music we'd like to capture a higher range of frequencies, up to say 20 kilohertz. So if music ranges up to 20 kilohertz, 22 kilohertz say, and Nyquist says sample at twice the highest frequency component, we should sample at 44 kilohertz. And in music we often will have stereo, 2 channels, left and right channel, and a typical sample size is 16 bits per channel. So the size of recording music at this quality, 44,000 times 16 bits, multiplied by 2 because we do that twice, one for the left channel, one for the right channel, for stereo. Consumes 1.4 megabits per second. How big is a CD? About 700 megabytes. How much music? If you buy the old style music CD, how much music, how many minutes can you fit on a CD? Anyone bought such a CD recently? 60 minutes, 70 minutes? This is the quality for CD at, from memory it's the quality for CD. "70 minutes is 70 times 60 seconds. If we record music at 1.4 megabits per second using this quality, then times 1.4 megabits, 70 minutes of music, 70 times 60 seconds, at 1.4 megabits per second is how many bits we'd need to store 70 minutes of music. What does it turn out to be? Anyone have a calculator? "70 times 60 times 1.4 equals 5,880 bits divided by 8. This is megabits per second, is about 700 or 735 megabytes. So on a CD, which is about this size, 700 megabytes, you can fit about 70 minutes of CD quality audio recorded on there. Because in CD, the typical audio quality is a sampling rate of 44 kilohertz, stereo 16 bits per channel. And in fact, that's specified in the standard for CDs, or audio CD. So an example of voice, typical quality of voice requires 64 kilobits per second. Audio, an example, is 1.4 megabits per second. What about standard definition digital TV? There are some variations, but an example resolution of standard definition digital is 720 by 576 pixels. 720 across, 576 down. 24-bit colour and 25 frames per second. So we repeat the images 25 times per second, multiply them together, 720 times 576 times 24 times 25 frames per second is about 250 megabits per second. Stream standard definition digital TV from some web server on the internet down to your TV at home. You need an internet connection that supports 250 megabits per second. Who has one? No one. Okay. This is, so to stream digital TV at standard definition quality, not high definition, you need 250 megabits per second, continuous. That's the amount of information contained in that video. High definition, resolution is much higher, the image is larger. 1.2 gigabits per second is needed to stream high definition TV. But those values are for the raw data without compression. In practice, we compress that data. Why? Compression reduces the capacity needed for storage. You want to store a lot of music on your hard drive, do not store it as CD quality at 1.5 megabits per second. Use some other codec that also includes compression, MP3 for example. Instead of your 70 minutes of music taking up 735 megabytes on your disk, using a different codec with compression, it may take up just 70 megabytes on your disk. Because within compression we can reduce the amount that we need, we reduce the number of bits we needed to store that information. Both storage and transmission. If I want to stream video across a network, instead of streaming at 1.2 gigabits per second for high definition TV, if that TV is compressed, then I may be able to stream at a much lower rate, tens of megabits per second. And it can be quite large gain with compression. It's not the intent of this topic to explain how compression works. Just classify and talk about the basics. We can say that with compression we have have either lossy compression or lossless compression. With lossy compression, we take our original information, apply some algorithm which may throw away some of the bits from the original information and produce an output compressed file or compressed data, which is of course should be smaller than the original data. How do we do compression? if we imagine a text file and we want to do compression, we look at patterns. We look at patterns in the input, and where some patterns repeat, we can replace them with smaller digital representations. Use less bits to store those patterns. If you have a large text file and it has the word hello in it many times, a large text file with the word hello in it many times, hello takes 5 bytes to store. 5 characters, 1 byte per character. Compression would see, okay, here's something that repeats quite often in our input. Let's replace this 5 bytes with some special code that represents hello. Assuming they're all letters, let's replace every instance of hello with a special character, the %sign, as a simple example. So we have everything the same. Instead of having hello here, we'd have this special character. So instead of storing hello, we store just 1 character. And on disk, instead of storing hello many times, we store the mapping, or if we know the mapping, we don't have to store it. If we know the compression algorithm, we have a mapping and we just store that replacement character, 1 byte on disk. So we've compressed some of the words from 5 bytes down to 1 byte. It's much more complex than that, but that's the idea, to take some structure that repeats in the input and replace it with a smaller digital representation in the output. There are different algorithms depending on whether it's text, whether it's audio or video. With lossy compression, some of the original information in the input is lost in the output. Take some input file and apply lossy compression. The output, when we apply lossy compression and then decompress to get the original input, the result after decompression will not be the same as the original input. That is, from the original input, when we compress it and then decompress, the result is different. We've lost some information. Lossless compression is if we take the input, compress, decompress, the resulting output here is identical to the original input. So we don't lose any information. But what's the common file compression algorithm you use? What do you use? File compression, what software? WinZip. So zip is a compression algorithm, zip. Is it lossy or lossless? Is it a lossy or lossless compression algorithm? It's lossless because you take your data, your file, you compress with zip. When you decompress, you get the exact same file again. If you didn't, you wouldn't be happy. Okay? It's a lossless compression algorithm. MP3 includes compression in the codec, and MP3 is a lossy compression algorithm. You take your original music, your original audio, apply MP3, you get some output, which is smaller, but when you decompress and play it back, it's not identical to what the original input was. We've lost some of the bits, and hence lost some of the quality. So we have lossy and lossless compression. Generally, lossy compression can compress more than lossless. And different algorithms have different capabilities to compact data. Some examples: lossy compression algorithms may be able to reduce data from its original size to around maybe 5 to 30% of its original size. Whereas lossless compression, we cannot compress so much. We may start with our original data and the output may be just 50% of the original size, half. Lossy compression compresses more in general. But lossy compression, we lose some quality, we lose some bits. How good can we compress different types of data depends upon the algorithm and what the data is. Normally we compress high motion video less than low motion video, because the compression of video normally depends upon the differences between frames. If each frame is very similar to the other one, we can compress that well. Like low motion video, where the frames are very much the same as they move. In high motion video, each frame has significant differences from the previous frame, and therefore we can compress less. So the data source impacts upon how much compression we can achieve. So for example, a sports video may not be able to compress as much as a talk show video, where there's not so much motion. Compressing low motion video is much better in terms of getting a final size smaller. That's all we're going to say about compression, just the difference between lossy and lossless, and it's commonly applied in data and multimedia communications. What about codecs? The last thing on this topic. A codec, you'll see in practice, refers to many different things. It sometimes refers to software or hardware or even a standard that performs the following operations of modulation, compression, formatting of a source from some analog into digital format. So a codec may be some software you have on your computer. It may be a standard that you would follow to implement that software, or it may be some hardware implemented in hardware on your computer. And it may do one or all of those different operations: modulate, compress, and format the source. Just some example, different codecs for different applications. You've seen or used many of them. In voice codecs, there are different ones which have require different data rates. PCM, some delta modulation, AD-PCM. Different codecs for different quality voice and use different amount of capacity. GSM phones, at least in the older version, used a codec which required a capacity of 14 kilobits per second, less than the normal 64 kilobits per second, but at a lower quality. Some audio codecs you would have no doubt used, and some lossy codecs, lossless codecs, you may have heard of some, and some video codecs. So common is H.264. It's just a name of a standard which specifies the algorithm for the codec, including compression. And then you also have heard of things like WAVE, AVI, MOV, OGG, and others. These are not codecs. These are what's called container formats. They specify how do we store that digital data. So inside a MPEG-4 container, we may have video encoded using different codecs. So the container may contain video using different codecs. So an AVI file does not specify the codec necessarily. You could have different codecs used to code that video. It gets confusing when you come across all these terms. But just some examples. So we have voice, audio, video applications. We know some basics of how they work. What do we need for good quality? Normal from the user's perspective, what's good quality? Some typical, not always, some typical data rates we need for voice and audio, tens to hundreds of kilobits per second. If we want to send audio across the network, then each stream we have in the order of tens to hundreds of kilobits per second. Video, we're talking about hundreds of kilobits per second up to tens of megabits per second, depending upon the quality. We said high definition TV requires, in the raw form, uncompressed, 1.2 gigabits per second. With compression, you can get that down to 10 megabits per second, tens of megabits per second. So compression aids a lot. That is, we save a lot of space with compression. What about errors? Most multimedia applications can tolerate some data loss, some smaller number of errors. I'll show a demonstration in a moment, if it works. That is, we send our data across the network. Some of the packets carrying that data are lost. The receiver doesn't receive them. The receiver can still play back that audio or video, in most cases without the user noticing. So some data loss, some errors are tolerated. What about delay? Interactive applications usually have strict delay requirements. That is, if the delay is much larger than these values, then the users will not be able to use those applications. Some typical numbers used for a voice call, if the delay between source and destination is less than 150 milliseconds, the users won't notice that. They'll think the quality is the same as if the two people were talking face to face. If it's between 150 to 400 milliseconds, they may notice the delay but can still talk, still have a conversation. Much larger than 400 milliseconds and it starts to become difficult to converse with someone. That is, the users have to modify their behaviour to talk. One talks and then waits for some period of time for the other to respond, and that becomes much harder to use. That's for interactive applications. For streaming applications, when we're sending from a server in one direction to a client, we can normally tolerate larger delays. We'll see some examples of how that's done. Most applications need small jitter if we want smooth playback of audio or video. Before going through that example, let's illustrate one. And at the same time, give you a few hints on the assignment for the last 20 minutes or so. What I'm going to do is stream some video between my two computers and see how different characteristics of the network support or impact upon the performance of video. Let me set this up. On the bottom, so I'm operating on my blue laptop. On the bottom, I'm going to log into the other laptop, if it works. The top one is 10.1.1.2. I'll draw this in a moment. And the bottom one is 10.1.1.3. So the scenario I have in this test two computers connected via an Ethernet cable. this. Computer 3 is going to be our server, the bottom one here, and computer 2 is going to be the client. 2. I have connected them via a 100 megabit per second Ethernet link. The delay, if I ping, the delay is about 400 milliseconds, 0.4 milliseconds, 400 microseconds. Is that right? So that's our network scenario, 2 computers connected. I'm going to stream, I have a video on this computer, and I'm going to use streaming to send it to the client and view it on the client. So the file is here, stream, and basically what the streaming is going to do is take the video, convert it into packets, send those packets across the network. When this computer receives it, the application takes those packets and the video in it and plays the video back. And then I'm going to do it when we change the characteristics of the network. That is, increase the delay and increase the packet loss, and see how that impacts on video. Let me remember how to do it. On the client, which is the white one, I'll just use VLC to play the video. By specifying the client's IP address and the port number 5004, because that's what the server will send to, using the protocol RTP. And in tomorrow morning we'll cover how RTP works. And on the server, use VLC on the command line and take a video, MP4, so the container format is MPEG, and stream it from the server to the client. And the commands I'm using, quite complicated, but they're given in one of the documentation for this software. I've just copied that. We specify to use RTP as the protocol to send the packets across the network. The destination in this case is our client, 10.10.1.2. The port number, and 5004, and how to multiplex the audio and video, and just the format of the multiplexing. You don't have to understand all those options. That's not the point. I'm going to start the server. It will start sending packets if everything works, and my laptop will receive those packets. I'll start the server and then start the client, and it started on the wrong screen on my... Did it work? No audio, it's just video in this case. We'll play it again in a moment so it comes out a bit clearer. What you're looking for is not the content, but look for any artifacts in the video, some pixelation anywhere. So it's streaming. I think the resolution is a little bit lower than standard definition digital TV. I'll play it again and just look for any artifacts in the video. Start the server again. I think that if you see this sort of Well, there's no bad artifacts yet. It's reasonably clear. So that's just changing between the scene. No noticeable artifacts in most cases. Some of the quality may not be so good because of my laptop, but we'll see in a moment what impacts upon quality. So that's with our link that supports 100 megabits per second and a round trip time or of a delay of 400 microseconds. Now I want to change my network. And what I'm going to do is on my receiver, let's see what happens when we drop some packets. Although it's not shown here, if we recorded and captured those files, we should be able to see how many packets are dropped. And I think you'll find that very few packets are dropped across this network. There's no reason for the packets to be dropped. But let's say, first 1% of the packets to be dropped. So of all the packets we send, streaming from server to client, we'll drop 1% of those packets. And see how that impacts, that is packet loss or errors, impact upon the quality of the video. How are we going to drop packets? Well, I can't introduce any problems in the link. We need some other software to drop packets. And what I'm going to use, and some of you have done the lab, on this computer, I'm going to use IP tables, which is some software that controls the packets coming into and out of the computer. And there are some options. If you haven't done the lab yet, you'll see it on Friday, but let's try. I'm going to add some rule using IP tables to the input so that the computer that receives the packets artificially drops some of those packets, drops, say, 1% of the packets, so that my video application doesn't receive them, and see how the video plays back. What's the command? Somewhere of the command shown here, you'll see it closer. We specify on packets coming into our computer, apply some statistical operation on, or use some statistics to drop packets with a probability in this example of 3%, 0.003, and randomly select packets to drop. So if I send 100 packets across the link, this command will tell my computer to randomly select some packets such that of those 100, 3 of them are dropped. They don't get received by the application. Let's set it at 1% to start. So now my receiver computer should drop 1% of the packets it receives. Let's try and play back our video. Start the server again and see if it impacts on the quality. Maybe you even saw a bit there. So look for artifacts. Okay. So now just 1% of the packets aren't getting to the receiver. It's playing back the video. It was. There we go. But you see the quality has significantly dropped. Almost unwatchable now. But some parts are okay. It depends a bit on the codec of how it can recreate the received image. So just 1% in that case caused reasonable degradation in the quality of the video at the receiver. So that's with packet loss. It would depend upon the network, it would depend upon the content being sent as to how much impact it has. In that case, just 1%. What about jitter? Remember, the delay or the variance between, or the difference between the delay of subsequent packets, average across all packets, is the jitter. The change in delay between packets. How does that impact on our application? Let's try. I will delete that so I no longer drop packets. Again, those that have done the lab will know the basics of that command. And now I want to try a different scenario. So you can use that in your experiments with TCP and UDP. Drop packets and see how that impacts on performance. Let's try something different. Our delay was 0.4 milliseconds. Let's make it 500 milliseconds, the delay. So that as if I send a packet, it takes 500 milliseconds to get there. And let's add some jitter. It's 500 milliseconds plus or minus 10 milliseconds. That is, the delay of the first packet is chosen between 490 and 510, somewhere randomly within that range. The next packet is within that range, but another random value, such that on average it's going to vary between 490 and 510, with an average delay of 500 milliseconds. Let's see how that impacts on our video. How do I add delay? Add delay. We need another command. And TC is the program that we can use. I'm going to use it on the server. If I can get the right window. Here we go. The black one is our server. TC is a program that manipulates the output queue of packets. The server sends packets. The packets are put in a queue to send out. TC can manipulate the packets in the queue, give priority for quality of service. Also, it can add some artificial delay to those packets, slow them down, that is, hold them in the queue for 500 milliseconds. Let's see how it works. On my server, use TC. We use a queuing algorithm or a queuing discipline. You don't have to remember the format. And we need to add some rule using my ETH0 device to emulate a network. That's what netm means, emulate a network. And the emulation is we want to add a delay of 500 milliseconds and a plus or minus 10 milliseconds. So my server is going to create packets, but then delay those packets. And then they'll be sent. Did I get it correct? Who missed that? Okay. Let's just check. Ping the client to the server. There's the ping time, 500 milliseconds. So now let's start our server. And then see how that impacts on the quality of our video. If the video starts. It's coming. So look for any artifacts in the video. Much better than when we had the packet drop. Packet drop we basically couldn't watch it. In fact, almost the same as the original case. This is a large delay, 500 milliseconds, has very little impact on the quality of that delay. Because when we'll see tomorrow that we use buffering, it may delay the start of the video, but once it starts playing, it's played smoothly. One last example before we finish today. On the server, let's remove that delay instead of add. Delete. So I no longer have that delay. And let's add same 500 millisecond delay, but let's increase the jitter. Instead of plus or minus 10, let's try plus or minus 200, a large jitter. The delay may be between 100 milliseconds and 700 milliseconds. So it goes up and down. And one more test. Ping. It's random, that is the operating system randomly chooses the delay. See, it's going up between 300 up to 700 milliseconds. Should be between 300 and 700. Now let's see if that impacts on our video. Let's hope it does. Start the server again to stream the video, and video starts. Maybe you see a little bit of freezing there, slow down in the motion, not easy to recognise. A little bit there, okay. You saw some of the pixelation on that video, most likely because of the jitter. And there again, you see the degradation in quality. So, very simple examples, but with packet loss, errors, our video sometimes can cope. In this example, it couldn't cope with just 1%. If we tried 0.5% or even lower, it may have coped okay. That is, we may not have noticed. So we can tolerate some errors, depending upon the content, not all. Delay for video streaming is not a problem normally. It may delay the start of our video, but not the quality. Jitter is a problem. If jitter is high, our quality at the receiver can go down. Tomorrow we'll explain some of those concepts again with some different examples on the slides. Jitter, delay, and so on.